How man became the master of the universe. The beginning of human curiosity and exploration. To understand how humans became masters of the universe, we must first examine the nature of human curiosity and the urge to explore. From our earliest ancestors gazing in wonder at the night sky, to modern astronauts traveling into the cold, silent void of space. The story of human mastery of the universe begins with our desire to understand the world around us. Long before humans developed complex technologies or scientific theories, they were observers of nature. Early human civilizations, such as the Sumerians, Egyptians, and Mayans, erected monuments aligned with the stars, created calendars based on the movements of celestial bodies, and used the sky to navigate their earthly environment. One of the earliest known astronomical records comes from the ancient Babylonians, who mapped the positions of planets and stars 2,000 years before Christ. They believed that the movements of these celestial bodies influenced events on Earth, a belief system that developed into astrology. Although astrology has been largely disproved by modern science, it demonstrates mankind's long-standing fascination with the heavens. Ancient civilizations also saw the universe as a source of myths and wonders. The Greeks, for example, believed that the gods lived among the stars, and their mythology was full of stories about cosmic battles, divine intervention, and the origin of the universe. These stories were not just for entertainment. They were an attempt to explain the cosmos and humanity's role in it. It was only when the ancient Greeks, in particular philosophers such as Pythagoras and Plato, began to question the purely mythological explanations of the universe that humanity made its first real progress towards a scientific understanding of the cosmos. Pythagoras proposed that the Earth was not flat but spherical, a radical idea for the time, based on his observations of lunar eclipses and the shadow cast by the Earth on the Moon. Aristarchus of Samos went one step further and proposed a heliocentric model of the universe around 300 years before Christ, although his ideas were only generally accepted over 1,000 years later with Copernicus. With their focus on geometry, mathematics, and observation, the early Greek astronomers laid the foundations for what would later become known as the scientific method. However, it was not until the 16th and 17th centuries, with the rise of the Renaissance and the beginning of modern science, that people began to seriously challenge their understanding of the cosmos. This period of history, known as the Scientific Revolution, marked a turning point in our relationship with the universe. In the year 1543, the Polish astronomer Nicholas Copernicus published his groundbreaking work De Revolutionibus Orbium Coelestium, in which he proposed a heliocentric model of the solar system. According to Copernicus, the Earth was not the center of the universe, rather it orbited the Sun together with the other planets. This idea was revolutionary as it challenged the long-standing geocentric model promoted by the Catholic Church, which viewed the Earth as the center of creation. Although Copernicus's ideas met with considerable resistance, they were later confirmed by astronomers such as Johannes Kepler and Galileo Galilei. Galileo, who was born at the beginning of the 70th century, the first man to use one of the first telescopes in the 19th century, observed moons orbiting Jupiter, craters on the Moon, and phases of Venus, evidence that supported the heliocentric model. These observations showed that not everything in the universe orbited the Earth and shook the belief in humanity's central position in the cosmos. The Copernican revolution was a decisive moment in human history. It marked the beginning of a shift from a universe defined by human-centered mythology and superstition to one based on observation, mathematics, and scientific inquiry. This transformation was crucial in paving the way for humanity's journey to become masters of the universe, not in the sense of dominance, but in our ability to understand, predict, and ultimately influence cosmic forces. Imagine living in a time before the heliocentric model of the universe was accepted. Every night you look up at the sky and watch the stars move predictably across the heavens. It seems obvious that the Earth is the center of everything, as everything seems to revolve around it. But then someone tells you that the Earth is actually moving through space, that it is just one of many planets orbiting the sun, and that the stars are incredibly far away. This idea is shocking and hard to believe. It challenges everything you have ever known about the universe. But over time, you begin to see the evidence. The movements of the planets don't quite fit the old model, and the night sky reveals new patterns when viewed through the prism of this radical theory. This thought experiment illustrates the profound change in perspective that took place during the Copernican revolution. Man was no longer at the center of the universe, and this realization was both sobering and liberating. It opened the door to a new era of exploration and discovery, an era that would ultimately allow us to understand the universe on a much larger scale. After the Copernican revolution, the scientific method became the main tool for understanding the cosmos. This method, developed by figures such as Galileo, Kepler, and Isaac Newton, emphasized observation, experimentation, and mathematical modeling. Through this method, mankind began to unravel the secrets of gravity, movement, and the laws that govern the universe. Isaac Newton, in particular, made groundbreaking contributions to our understanding of the universe. In the year 1687, he published Philosophia Naturalis Principia Mathematica, in which he described the laws of motion and the law of universal gravitation. Newton's law of gravity explained why objects fall to the Earth, why the planets orbit the Sun, and why the Moon remains in the Earth's orbit. His work showed that the same physical laws that apply on Earth also govern the movement of celestial bodies, a union that represented a significant step in mankind's understanding of the cosmos. Imagine you are Isaac Newton sitting under an apple tree when an apple falls to the ground. This simple event makes you think, why do objects fall? What force pulls them to Earth? As you think about it, you realize that the same force that pulls the apple down is also the force that keeps the Moon in its orbit around the Earth and the planets orbiting the Sun. This is the force of gravity, and it acts not only on Earth, but in the entire universe. This thought experiment illustrates the importance of Newton's insight, that the same laws of physics apply everywhere, from the smallest objects on Earth to the largest celestial bodies in the universe. This realization laid the foundation for modern physics and enabled mankind to begin its search for a deeper understanding of cosmic forces. In the 20th century, human curiosity and scientific progress had reached a new peak, the space age. In 1957, the Soviet Union launched Sputnik, the first artificial satellite into orbit around the Earth. This event marked the beginning of direct space exploration by mankind. Less than a decade later, in 1961, Soviet cosmonaut Yuri Gagarin became the first human to orbit the Earth, demonstrating that humans could not only observe the cosmos, but also physically travel beyond our planet. The pinnacle of human space exploration came in 1969, when NASA's Apollo 11 mission successfully landed humans on the Moon. Neil Armstrong's famous words, That's one small step for man, but one giant leap for mankind, marked a monumental achievement in human history. For the first time, mankind set foot on another celestial body, marking the beginning of our journey to become masters of space. Imagine you are standing on the surface of the moon and looking back at the Earth. The planet appears as a small blue and white ball floating in the blackness of space. From this vantage point, you realize how fragile and small the Earth really is, surrounded by the endless expanse of the universe. This view gives you a new perspective on humanity's place in the cosmos, a perspective that is humbling, but also full of potential. This thought experiment captures the awe-inspiring nature of human space exploration and illustrates that although we are small in the grand scale of the universe, we are still capable of extraordinary feats. The space age marked humanity's first steps in exploring and understanding the cosmos, but it also showed how much there is still to learn. There is a compelling argument that humanity has indeed become masters of the universe, at least in the sense that we have developed the ability to understand and influence natural forces. Through the application of the scientific method, mankind has deciphered the laws of physics, explored the furthest reaches of our solar system, and developed technologies that allow us to observe distant galaxies and black holes. We have created artificial satellites that orbit the Earth, space probes that travel beyond the solar system, and telescopes that look deep into the cosmos and capture light from billions of years ago. Our knowledge of the universe has expanded exponentially, and we now have a better understanding of phenomena such as dark matter, black holes, and the Big Bang than ever before. Humanity's technological advances have also enabled us to manipulate matter at a microscopic level, such as through the development of quantum mechanics, particle physics, and the discovery of the Higgs boson. In this sense, humanity has not only mastered its immediate surroundings, but has also begun to decipher the basic building blocks of the universe. Are we really masters? However, although humanity has made remarkable progress, the argument that we are masters of the universe is not without its challenges. Despite our progress, there is still a lot we don't understand about the universe. Dark matter and dark energy, two of the most common substances in the universe, remain largely mysterious. We cannot yet fully explain what black holes are, how the universe came into being, or whether there is life beyond Earth. Moreover, our control of the universe is limited by our technological limitations. While we have sent probes to distant planets and set foot on the moon, human space travel is still limited to our immediate cosmic neighborhood. The infinite expanse of the universe remains largely unexplored, and interstellar travel, let alone mastery of the entire cosmos, is still beyond our reach. There is also the argument that our understanding of the universe is at best a small glimpse into a much larger and more complex reality. As quantum mechanics and the theory of relativity show, the deeper we delve into the nature of the universe, the more we discover that reality is often based on principles that are counterintuitive and difficult to grasp. This suggests that our current knowledge is only the beginning of a much longer journey towards understanding. The expanding universe and the human search for understanding. To further explore how humans might be considered masters of the universe, we must consider one of the most profound discoveries of the 20th century, the realization that the universe is expanding. This discovery fundamentally changed our understanding of the cosmos and raised new questions about the origin, evolution, and ultimate fate of the universe. In this chapter, we will explore the scientific breakthroughs that led to the discovery of the expanding universe and how these findings have contributed to our evolving relationship with the cosmos. At the beginning of the 20th century, most scientists believed that the universe was static and unchanging. The prevailing view was that the stars and galaxies were firmly anchored in space and that no large-scale movements were taking place. However, this perspective was to change dramatically in the 1920s, thanks to the work of the American astronomer Edwin Hubble. Hubble's observations, which he made with the powerful Hooker telescope at the Mount Wilson Observatory in California, revealed something extraordinary. In the year 1924, he proved that what were previously thought to be nebulae, gas clouds within our galaxy, were in fact entire galaxies that lay far beyond the Milky Way. This discovery alone increased the known size of the universe by an unimaginable factor. But Hubble's most significant discovery came a few years later. By studying the light from distant galaxies, Hubble discovered that almost all of them were moving away from us. This was recognizable by the redshift effect in the light spectrum of these galaxies, a phenomenon in which light waves are stretched as objects move away from an observer, shifting the light towards the red end of the spectrum. 1929 Hubble formulated what is now known as Hubble's law, which states that the further away galaxies are from us, the faster they move away from us. This discovery was the first concrete proof that the universe is expanding. It refuted the long-held belief in a static universe and introduced the idea that the cosmos has a dynamic history. Hubble's discovery of an expanding universe inevitably led to an important question. If the universe is expanding, what does that tell us about its past? The idea that emerged from this consideration is known today as the Big Bang Theory. The Big Bang Theory states that the universe began around 13.8 billion years ago as an incredibly hot and dense point, often referred to as a singularity. From this singularity, the universe began to expand, and it has been expanding ever since. The evidence supporting this theory is not only Hubble's observation of an expanding universe, but also the discovery of cosmic microwave background radiation, faint remnants of heat from the early universe, first detected in 1964 by Arno Penzias and Robert Wilson. The Big Bang Theory changed human understanding of the universe. It indicated that the universe had a beginning, a moment of creation, and that it has been evolving ever since. This realization has profound implications for our understanding of time, space, and matter. It also places humanity in a much larger cosmic narrative in which the events that shaped the early universe continue to influence the structure and behavior of galaxies, stars, and planets. Imagine you had the ability to rewind time and watch the universe contract rather than expand. As you turn back time, the galaxies move closer together. Stars form in rapid bursts, and the fabric of space itself shrinks. Eventually, you reach a point where all matter and energy are concentrated in an incredibly small, hot, and dense point, the singularity from which the universe emerged. In that moment, time ceases to exist, and you are left to contemplate the profound mystery of what was before that moment. This thought experiment illustrates the concept of the Big Bang and how the universe has been expanding for billions of years. It also raises philosophical questions about the nature of time and existence and reminds us of the limits of our current knowledge and the mysteries that remain. Despite the incredible progress made in understanding the expansion of the universe, there are still many unanswered questions. Two of the greatest mysteries of modern cosmology are dark matter and dark energy, two phenomena that seem to dominate the universe but are largely invisible and poorly understood. Dark matter was first suspected in the 1930s by the Swiss astronomer Fritz Zwicky, who noticed that galaxies and galaxy clusters moved much faster than could be explained by the visible matter in these galaxies. He concluded that there must be a form of invisible matter that provides additional gravitational force. This became known as dark matter. Since then, numerous observations have confirmed the existence of dark matter, which makes up around 85% of the matter in the universe. Despite its abundance, dark matter has never been directly observed. It does not emit, absorb, or reflect light, which makes it invisible to traditional telescopes. Scientists know that it exists because it exerts its gravitational effect on visible matter, but its true nature remains a mystery. Dark energy, on the other hand, was only discovered more recently. In the late 1990s, two independent teams of astronomers discovered that the expansion of the universe was not slowing down as expected. It was accelerating. This discovery was made by observing distant supernovae that appeared fainter than they should have been. The only explanation was that an unknown force, called dark energy, was driving the accelerated expansion of the universe. Together, dark matter and dark energy make up more than 90% of the universe. However, despite their overwhelming influence, we still know very little about them. This is a humbling reminder that although humanity has made extraordinary progress in understanding the cosmos, we are still far from mastering its most basic components. Imagine for a moment that you live in a galaxy that consists almost entirely of dark matter. You can't see the stars or planets, but you can feel their gravitational effects all around you. Your world is governed by forces that you cannot directly observe, and the fabric of your existence is shaped by invisible matter. In this galaxy, your understanding of the universe would be limited by things you cannot see, just as our own understanding is shaped by the mysterious nature of dark matter and dark energy. This thought experiment emphasizes how much of the universe is still hidden from us and how the forces that dominate cosmic evolution are still beyond our full understanding. Despite the mysteries of dark matter and dark energy, humans have developed a variety of powerful tools to explore the universe. Telescopes, space probes, and other technologies allow us to observe distant galaxies, study the behavior of black holes, and even detect gravitational waves, ripples in space-time caused by the collision of massive objects such as black holes or neutron stars. The Hubble Space Telescope, which was launched in 1990, is one of the most important tools of modern astronomy. It has provided breathtaking images of distant galaxies, nebulae, and star-forming regions, as well as collecting crucial data on the expansion of the universe. Hubble's observations have refined our understanding of the age of the universe, the rate of its expansion, and the processes that govern the formation of stars and planets. In recent years, new technologies have extended the boundaries of what we can observe. The James Webb Space Telescope, which will act as the successor to Hubble, will enable us to look even deeper into the history of the universe and observe the formation of the first stars and galaxies. Meanwhile, in 2019, the Event Horizon Telescope provided mankind with the first image of a black hole, giving us a glimpse into one of the most extreme environments in the universe. Imagine using the James Webb Space Telescope to look back to the first few 100 million years after the Big Bang. They observe the birth of the first stars, massive and short-lived, which fuse hydrogen into helium and produce the first heavy elements. These stars burn brightly and then explode into supernovae, scattering their material across the universe and initiating the formation of galaxies. Through this telescope, you will witness the universe in its childhood, a time when it was much denser, hotter, and more chaotic than today. This thought experiment demonstrates the power of modern technology to transport us through time and space and allow us to observe the earliest moments of the universe's existence. It also emphasizes the ongoing nature of the human search for a deeper understanding of the cosmos. There are convincing arguments that humans are gradually becoming masters of the universe, at least in the sense that we can increasingly study, observe, and understand it. The discovery of the expanding universe, the development of the Big Bang theory, and the identification of dark matter and dark energy represent extraordinary advances in our understanding of the cosmos. Our ability to develop sophisticated technologies, such as telescopes, space probes, and particle accelerators, has enabled us to explore the universe in ways that were unimaginable just a few centuries ago. We have unlocked many secrets of the stars, mapped the movements of galaxies, and even detected the faint echoes of the birth of the universe. Nevertheless, despite these advances, there are vast areas of the universe that are still beyond our reach, both physically and conceptually. Dark matter and dark energy, which together make up the majority of the universe, remain largely unexplored. We don't know what they are, how they work, or what their existence means for the future of the cosmos. In addition, our technological tools, however powerful they may be, are still limited. Even the most advanced telescopes can only observe a small part of the universe, and much of what we know is based on indirect evidence. We have sent probes to the furthest reaches of our solar system, but interstellar travel remains a distant dream. The sheer size of the universe, billions of light years in diameter, means that most of it is currently beyond our ability to explore. The rise of quantum mechanics and humanity's control over the microcosm. While humanity has made remarkable progress in understanding the vastness of the universe through the discovery of cosmic phenomena such as black holes, dark matter, and the expanding universe, there is an entirely different frontier that has also led us to become masters of the universe, the quantum world. The deeper we delve into this microscopic realm, the more the mysteries of quantum mechanics reveal a strange and counterintuitive side of reality that turns classical understanding on its head. In this chapter, we will explore how quantum mechanics has revolutionized human knowledge and the unprecedented control it gives us over the fundamental building blocks of the universe. The early 20th century brought one of the most profound revolutions in science, the development of quantum mechanics. At the heart of quantum mechanics is the idea that the behavior of particles on the smallest scales, such as electrons, photons, and atoms, is determined by probabilities, uncertainties, and the strange rules of quantum theory. This was in stark contrast to classical physics, in which objects behaved in a predictable way and their positions and speeds could be measured precisely. The foundations of quantum mechanics were laid by Max Planck in the 1900s when he introduced the idea of energy quanta to explain black-body radiation. Shortly afterwards, in the year 1905, Albert Einstein provided further evidence of the need for a new theory with his explanation of the photoelectric effect, which showed that light acts as both a wave and a particle. In the following decades, scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger further developed the principles of quantum mechanics, which fundamentally changed our understanding of nature. One of the best-known aspects of quantum mechanics is Heisenberg's uncertainty principle, which was introduced in the year 1927. This principle states that there is a fundamental limit to how precisely we can know certain pairs of properties of a particle, such as its position and momentum, simultaneously. The more precisely we know the position of a particle, the less we know about its momentum, and vice versa. This blurring is not due to technological limitations, but is an inherent characteristic of nature. At the quantum level, particles have no fixed positions or velocities until they are observed. Instead, they exist in a state of superposition in which all possible outcomes coexist as probabilities. Only when we measure the system does the superposition collapse into a solid state. This discovery had a profound impact on the philosophy of science. The classic idea that the universe works like a predictable clockwork machine has been shattered. Instead, reality at the quantum level is determined by probabilities and uncertainties, which introduces a certain randomness into the fundamental laws of nature. To illustrate the strange implications of quantum mechanics, the physicist Erwin Schrödinger developed a famous thought experiment known as Schrödinger's cat. In this experiment, a cat is placed in a sealed box together with a vial of poison that is released when a radioactive particle decays. According to quantum mechanics, the radioactive particle is in a superposition of decay and non-decay until it is observed. This means that the cat is both alive and dead at the same time until someone opens the box and observes the result. This thought experiment illustrates the counterintuitive nature of quantum mechanics, in which particles can exist in several states simultaneously. It challenges our classical understanding of reality and forces us to confront the strange and often paradoxical behavior of the quantum world. Another amazing feature of quantum mechanics is the phenomenon of quantum entanglement. When two particles are entangled, their properties are linked in such a way that the state of one particle immediately affects the state of the other, regardless of how far apart they are. This connection occurs faster than the speed of light, which prompted Albert Einstein to describe it as a spooky action at a distance. Entanglement has been confirmed in numerous experiments, but remains one of the most puzzling aspects of quantum theory. How can two particles communicate with each other instantaneously over long distances? The answer lies in the non-local nature of quantum mechanics, in which particles do not follow the classical notions of space and time. Instead, entangled particles behave as a single, unified system, even if they are widely separated from each other. Imagine you have two entangled particles, one in your laboratory on Earth and the other on a spaceship halfway across the galaxy. If you measure the state of the particle in your laboratory, you immediately know the state of the particle on the spaceship, even though it is light years away. This phenomenon does not involve a physical signal traveling between the particles, and yet their states remain perfectly correlated. The implications for communication and the transmission of information are profound, even if the limitations of relativity continue to prevent information from being transmitted faster than light. This thought experiment shows the strange and fascinating nature of quantum entanglement. It challenges our classical ideas about how information is transmitted and suggests that the universe is far more interconnected at the quantum level than we ever imagined. One of the most exciting applications of quantum mechanics is the development of quantum computing. Unlike classical computers, which use bits as the basic unit of information, where each bit is either a 0 or a 1. Quantum computers use qubits, which can exist simultaneously in a superposition of 0 and 1. This enables quantum computers to perform many calculations simultaneously and significantly increase their computing power for certain tasks. Quantum computing has the potential to revolutionize areas such as cryptography, materials science, and artificial intelligence. One of the best-known algorithms that could benefit from quantum computing is Shor's algorithm, which can factorize large numbers exponentially faster than any known classical algorithm. This has significant implications for encryption, key cracking, and cybersecurity. The development of quantum computers also demonstrates mankind's growing control over the quantum realm. By utilizing the principles of superposition and entanglement, scientists are beginning to manipulate the fundamental building blocks of reality and push the boundaries of what is possible in computation, information processing, and problem solving. Imagine you are working on a problem that would take a classical computer billions of years to solve. With access to a fully functional quantum computer, you enter the problem and within seconds, the solution appears on the screen. The quantum computer has used its ability to perform many calculations simultaneously and solve the problem in a fraction of the time a conventional machine would have taken. This thought experiment illustrates the enormous potential of quantum computing and how it represents a new frontier in human control over the fundamental processes of the universe. While quantum computers are still in the early stages of development, their potential to revolutionize industries and scientific research is immense. One of the most controversial interpretations of quantum mechanics is the many worlds interpretation, which was first proposed by physicist Hugh Everett in the 1950s. According to this theory, every time a quantum event occurs, the universe splits into several parallel realities in which each possible outcome exists in its own separate universe. For example, if you flip a coin, there is a universe in which the coin lands on heads and another universe in which it lands on tails. In this interpretation, the universe we experience is just one of an infinite number of parallel worlds, all of which are equally real. Every possible outcome of every quantum event creates a new branch of reality and leads to a multiverse full of possibilities. The many worlds interpretation has profound implications for our understanding of reality. If it is true, it means that there are countless versions of us living different lives in different parallel universes. It also means that the concept of probability, which is so central to quantum mechanics, can be understood as a reflection of the many realities that exist simultaneously. Imagine that every time you make a decision, the universe splits into several parallel realities. In one universe, you decide to become a scientist, while in another, you become an artist. As you continue to make choices throughout your life, an infinite number of parallel worlds emerge, each representing a different version of you and a different path you have taken. This thought experiment illustrates the astonishing effects of the many worlds interpretation. If true, it suggests that the universe is far more complex than we could ever comprehend, with an infinite number of possibilities playing out in countless parallel realities. There is a convincing argument that humanity is on its way to mastering the quantum world. Through our understanding of quantum mechanics, we have developed technologies that allow us to manipulate particles on the smallest scales. Quantum computing, quantum cryptography, and advances in particle physics show that we are beginning to harness the power of the quantum realm in ways that were previously unthinkable. In the coming decades, mastering quantum mechanics could lead to breakthroughs in energy production, medicine, material science, and much more. As we continue to explore the strange and counterintuitive world of quantum particles, humanity's control over the fundamental building blocks of the universe will only continue to grow. But despite our growing understanding of quantum mechanics, there is still a lot we don't know. The true nature of quantum phenomena such as entanglement, superposition, and the collapse of the wave function remains a mystery, and many of the questions raised by quantum mechanics are deeply philosophical. Furthermore, quantum mechanics challenges the fundamental notion of determinism and predictability, and suggests that the universe is determined by probabilities rather than certainties at the smallest scales. This randomness brings an element of unpredictability to the universe that could limit our ability to fully master it. Finally, the many worlds interpretation, if correct, suggests that humanity's control over the universe is limited to a single branch of an infinite multiverse. While we may be able to manipulate particles and predict their behavior in our own reality, the countless parallel worlds that exist alongside ours remain hidden from us. The age of space travel, the reach of mankind beyond Earth. As humanity's understanding of the universe deepened through the development of astronomy, physics, and quantum mechanics, the next logical step was to extend our physical reach beyond our home planet. The age of space travel marked a new chapter in our journey to master the universe. It was the time when mankind first escaped Earth's gravity and ventured into the unknown, turning what was once science fiction into reality. In this chapter, we will explore how human space exploration has evolved over the last century, the scientific breakthroughs that have been achieved, and the future possibilities that lie beyond. The history of modern space travel begins with the geopolitical tensions of the Cold War. In the 1950s, the United States and the Soviet Union were in fierce competition for technological superiority. This competition extended into space and triggered what became known as the space race. The first significant milestone in this race occurred in 1957, when the Soviet Union successfully launched Sputnik, the world's first artificial satellite. Sputnik orbited the Earth every 96 minutes and sent out radio signals that could be received by anyone with the appropriate equipment. Although the satellite itself was relatively simple, its launch had a profound effect. It showed that mankind had developed the technology to send objects into space and marked the beginning of a new era. The United States responded with its own space program, and competition between the two superpowers intensified. In 1961, Soviet cosmonaut Yuri Gagarin became the first man to orbit the Earth, consolidating the Soviet lead in the space race. Gagarin's historic flight only lasted 1 hour and 48 minutes, but it was a monumental achievement. For the first time, mankind had left the surface of the Earth and ventured into space. Although the Soviet Union achieved early success, the United States ultimately claimed the most iconic victory in the space race, the first manned landing on the Moon. In the year 1961, President John F. Kennedy's famous challenge to put a man on the Moon and bring him safely back to Earth before the end of the decade. This ambitious goal led to the creation of NASA's Apollo program. The Apollo missions culminated on July 20, 1969, when Apollo 11 astronauts Neil Armstrong and Buzz Aldrin walked on the Moon. As Armstrong descended the ladder of the lunar module and set foot on the dusty surface of the moon, he uttered the now famous words, "That's one small step for a man, but one giant leap for mankind." The moon landing was a technological and logistical triumph and represented the pinnacle of human achievement in space travel up to that point. The Apollo program not only fulfilled Kennedy's challenge, but also provided valuable scientific data on the composition, history, and geology of the moon. Over the course of 6 manned landings, a total of 12 astronauts set foot on the lunar surface, collecting samples and conducting experiments that deepened our understanding of the Earth-Moon system. Imagine sitting in front of a black-and-white television on July 20, 1969, watching live footage of Neil Armstrong walking on the surface of the moon. The blurred images from hundreds of thousands of kilometers away seem both surreal and awe-inspiring. You experience history in real time, the first human being to set foot on another celestial body. When you think of the technological achievements that have made this possible, you realize that humanity has crossed a threshold. We are no longer confined to Earth, but are becoming explorers of the wider universe. This thought experiment captures the emotions of the millions of people who watched the moon landing. For many, it symbolized the incredible potential of human ingenuity and the possibility of going even further into space. In the years following the Apollo missions, NASA sought to develop a new type of spacecraft that could be reused for multiple missions to reduce the cost of space travel. This led to the development of the Space Shuttle, a revolutionary spacecraft that could launch into orbit, return to Earth, and be flown again. The Space Shuttle program began in 1981 with the launch of Columbia and carried out a total of 135 missions over the next 3 decades. Thanks to its versatility, the shuttle was able to transport astronauts, satellites, and scientific equipment into space, and played a key role in the construction of the International Space Station, ISS. One of the most important missions of the Space Shuttle program was the deployment of the Hubble Space Telescope in 1999. Hubble provided some of the most detailed and impressive images of distant galaxies, nebula, and star clusters, and offered new insights into the structure and history of the universe. Although the Space Shuttle program has faced challenges, including the tragic losses of the Challenger in 1986 and the Columbia in 2003, it remains a testament to human commitment to space exploration. The program laid the foundation for future ventures and inspired a new generation of scientists and engineers. Imagine you are an astronaut on board the Space Shuttle, sitting in the cockpit as the countdown counts down to 0. The powerful engines roar and you feel the enormous acceleration force as the shuttle lifts off from the launch pad. Imagine hurtling through the atmosphere at a speed of over 25,000 kilometers per hour in a matter of minutes and feeling the crushing weight of G-forces before you reach weightlessness in orbit. When you look out of the window, you can see the curvature of the Earth below you and the vast blackness of space above. They are among the chosen few who have left the confines of Earth and ventured into space. This thought experiment shows the unique experience of a spaceflight and the breathtaking views that astronauts experience. It also highlights the technical expertise required to build and operate spacecraft that can carry humans into orbit and beyond. In the 1990s, space agencies from all over the world, including NASA, Roscosmos, Russia, ESA, Europe, JAXA, Japan, and CSA, Canada, came together to build the International Space Station, ISS. It was started in stages and has been continuously inhabited since the year 2000. The ISS serves as a microgravity laboratory in which scientists can carry out experiments in physics, biology, medicine, and other fields. The ISS orbits the Earth approximately every 90 minutes, moving at over 27,000 kilometers per hour. Astronauts on board the station experience weightlessness, which enables them to study the effects of long-duration flights on the human body and carry out experiments that would not be possible under the influence of the Earth's gravitational pull. One particularly important aspect of the ISS is its role in international cooperation. For more than 2 decades, astronauts from all over the world have been living and working together on the station, sharing scientific knowledge and expanding humanity's understanding of space. The ISS also serves as a testbed for technologies that will be crucial for future missions to the Moon, Mars, and beyond. Imagine you are an astronaut on board the ISS, floating in zero gravity as you go about your daily tasks. Outside the window, you can see the Earth rotating beneath you, with its oceans, continents, and clouds spreading out in front of you. Every 90 minutes, you will experience a sunrise or sunset as the station completes another orbit around the Earth. You spend your days conducting experiments, maintaining the station's systems, and communicating with scientists on Earth. Life in space is challenging, but also offers a unique perspective on the fragility of the Earth and the vastness of outer space. This thought experiment provides an insight into the daily life of astronauts on board the ISS. It also underlines the importance of space stations, such as the ISS, in preparing humanity for longer journeys through the solar system. As we look to the future, humanity's ambitions in space continue to grow. NASA's Artemis program aims to return up to 2,025 humans to the Moon, with the long-term goal of establishing a sustainable presence on the lunar surface. This will serve as a springboard for future missions to Mars, where scientists hope to find evidence of past or present life and learn more about the planet's history. Private companies such as SpaceX, Blue Origin, and others are also playing an increasingly important role in space travel. SpaceX's Starship, currently under development, is designed to be a fully reusable spacecraft capable of taking humans to Mars and beyond. The rise of commercial space travel is accelerating humanity's ability to explore the solar system and opening up new opportunities for space tourism, asteroid mining, and the colonization of other planets. In addition to these short-term goals, scientists are also looking further into the future. Missions to the outer planets, such as Jupiter, Saturn, and their moons, promise new insights into the formation of the solar system and the potential for life beyond Earth. The search for exoplanets, i.e., planets orbiting other stars, has also become an important focus of modern astronomy. With the discovery of thousands of exoplanets, including some with potentially life-friendly conditions, the search for extraterrestrial life is more promising than ever. Imagine you are part of the first manned mission to Mars. After a months-long journey, your spaceship reaches the orbit of Mars, and you prepare to land on the planet's surface. As the landing unit touches down in the red Martian dust, you get out and feel the light gravity of Mars pulling you down. Around you, the landscape is barren and windswept, but the knowledge that you are standing on another planet fills you with awe. They begin to explore the surface, collect samples, and set up equipment for future missions. You are part of the next phase of human exploration, a pioneer on the way to becoming an interplanetary species. This thought experiment captures the excitement and challenges of humanity's future space travel. As we move further and further away from Earth, we will face new obstacles. but we will also gain a deeper understanding of our place in the cosmos. The argument that humanity is becoming master of the universe is supported by our achievements in space travel. In just a few decades, we have progressed from sending simple satellites to landing humans on the moon, building space stations and launching probes to the furthest reaches of the solar system. Our understanding of the cosmos has expanded dramatically, and we now have the technology to explore other planets, moons, and even interstellar space. In addition, the rise of commercial space travel is accelerating progress and making space more accessible than ever before. With the combined efforts of government space agencies and private companies, humanity stands poised to continue exploring the universe and potentially establish a permanent presence beyond Earth. However, there are significant challenges that still need to be overcome. While mankind has explored a small part of space, the majority of the universe remains inaccessible. The distances between stars, even within our own galaxy, are so immense that interstellar flight may still be centuries away, if it ever becomes possible at all. The idea of mastering the universe implies a level of control and understanding that we have not yet achieved and may never fully achieve. Furthermore, the dangers of space travel are enormous. Radiation, microgravity, and the psychological effects of long-term missions are just some of the obstacles that must be overcome before humanity can establish a sustainable presence on other planets. Although we are making progress, the challenges that lie ahead are enormous. The search for extraterrestrial life. Are we alone in the universe? One of the most profound questions humanity has ever asked itself is whether we are alone in the universe. As our knowledge of the cosmos has grown, so has our curiosity about the possibility of extraterrestrial life. The search for life beyond Earth is no longer limited to science fiction. It has become a central focus of modern astronomy, biology, and planetary research. In this chapter, we will explore the scientific efforts to find life elsewhere in the universe, the methods used to search for extraterrestrial civilizations, and the philosophical implications that a discovery or lack of discovery of life beyond our planet might have. In the year 1961, astronomer Frank Drake formulated an equation to estimate the number of technologically advanced civilizations in our galaxy that are capable of communicating with us. This equation, known as the Drake equation, takes into account several factors, such as the rate of star formation, the proportion of stars with planets, the number of planets that could potentially support life, and the likelihood of intelligent life emerging and developing technology capable of interstellar communication. The Drake equation is not intended to provide a definitive answer, but rather to guide scientific thinking about the factors that influence the emergence of intelligent life. It has inspired decades of research, with each new discovery in astronomy, planetary science, and biology, expanding our understanding of the conditions that could potentially give rise to life. As we continue to discover more exoplanets, planets orbiting stars outside our solar system, the number of potentially habitable worlds in our galaxy is growing. However, many of the factors in the Drake equation remain highly uncertain. Although we know that life originated on Earth, we do not know how frequently or rarely such an event could occur elsewhere. In recent decades, the discovery of thousands of exoplanets has revolutionized our understanding of planetary systems. The first exoplanet around a sun-like star was discovered in 1995, and since then, missions such as the Kepler Space Telescope and TESS, Transiting Exoplanet Survey Satellite, have uncovered a staggering variety of planets beyond our solar system. Some of these exoplanets are in the habitable zone, the region around a star where conditions could exist that allow liquid water to exist on the surface of the planet, which is considered a key prerequisite for life as we know it. One of the most exciting discoveries in recent years has been the detection of 7 Earth-sized exoplanets orbiting the star TRAPPIST-1, which is about 40 light-years away from Earth. 3 of these planets are located in the star's habitable zone, which raises the possibility that they could have life-friendly environments. In addition to size and location, astronomers also study the atmospheric composition of exoplanets and look for signs of gases such as oxygen, methane, and carbon dioxide, which could indicate biological processes. Although we have not yet found definitive evidence of life on an exoplanet, the sheer number of potentially habitable worlds in our galaxy suggests that the search has only just begun. As our observational technologies improve, we may one day discover clear signatures of life, or even signs of advanced civilizations on distant worlds. Imagine astronomers using the James Webb Space Telescope to discover the atmosphere of an Earth-sized exoplanet in the habitable zone of its star. As they analyze the data, they find clear signs of oxygen, methane, and other gases that would be difficult to explain without biological activity. This discovery sends shockwaves through the scientific community and the entire world. For the first time, we have evidence of life beyond Earth, even if we cannot observe it directly. How would this discovery change our understanding of the universe and our place in it? This thought experiment illustrates the potential impact that the discovery of life on another planet could have. Such a discovery would fundamentally change human perception and raise profound questions about the nature of life in the universe. While the search for microbial life on distant planets is a major focus of astrobiology, there is another aspect of the search for life that is even more tantalizing: the search for extraterrestrial intelligence, SETI. SETI focuses on the search for signals or evidence of advanced civilizations beyond Earth. The idea is that if intelligent civilizations exist elsewhere in the galaxy, they might use radio waves or other forms of communication that we could detect from Earth. Since the 1960s, radio telescopes have been used to scan the sky for signals that could indicate the presence of an extraterrestrial civilization. One of the most famous events in the history of SETI occurred in 1977, when astronomer Jerry Eman detected a strong and unusual radio signal from deep space using Ohio State University's Big Ear radio telescope. This signal, known as the WOW signal, lasted 72 seconds and has never been conclusively explained, but remains a point of fascination in the search for extraterrestrial intelligence. Despite the great efforts invested in SETI, no confirmed signals from extraterrestrial civilizations have yet been detected. This raises important questions about the likelihood of intelligent life elsewhere in the galaxy, and whether civilizations like ours are common or extremely rare. Where is everyone now? The lack of evidence for extraterrestrial civilizations has led to a famous question known as the Fermi paradox, named after physicist Enrico Fermi. In the 1950s, Fermi asked a simple but profound question: if intelligent extraterrestrial civilizations exist, where are they? Given the age of the universe, the large number of stars and planets, and the possibility of advanced civilizations developing space travel, why haven't we seen any signs of them? There are many possible answers to the Fermi paradox. One possibility is that intelligent civilizations are extremely rare or short-lived, meaning that intelligent life could emerge but not survive long enough to spread through the galaxy. Another explanation is that advanced civilizations may use forms of communication that we are not yet able to recognize or understand. There is also the possibility that civilizations exist but choose not to reveal themselves. Some speculate that advanced civilizations may maintain a galactic quarantine and intentionally avoid contact with less advanced civilizations like ours to allow for natural evolution and development. The Fermi paradox remains one of the most puzzling questions in the search for extraterrestrial life. While the universe appears vast and full of possibilities, the silence from the stars suggests that there are either significant barriers to the development of intelligent life, or we have not yet developed the tools to recognize it. Imagine that scientists in a SETI observatory receive a clear, repeating signal from a distant star system. After weeks of analysis, they come to the conclusion that the signal is artificial, proof of an advanced extraterrestrial civilization. The discovery is announced to the world and triggers excitement, fear, and countless questions. How would humanity react to the knowledge that we are not alone in the universe? Would we try to communicate with the extraterrestrial civilization, or would we remain silent for fear of possible consequences? This thought experiment underscores the profound impact that the discovery of an intelligent extraterrestrial civilization would have on human society. It would challenge our understanding of life, technology, and the future of our own civilization. While the search for extraterrestrial intelligence focuses on distant stars and galaxies, scientists are also looking for signs of life that could be much closer to Earth. Several moons in our solar system are considered promising candidates for harboring life, in particular Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. Both moons are thought to have oceans beneath their ice crusts, which could possibly provide the necessary conditions for life. NASA's Galileo mission, which studied Jupiter and its moons in the 1990s, provided evidence that Europa has a vast ocean beneath its frozen surface, which may contain twice as much water as all of Earth's oceans combined. Similarly, the Cassini mission showed that Enceladus has active geysers that eject water and ice particles into space, indicating the presence of a liquid ocean beneath its ice shell. These findings make Europa and Enceladus prime targets for future missions aimed at searching for signs of life. In the coming decades, planned missions such as NASA's Europa Clipper mission will investigate the habitability of these moons in more detail. Imagine a robotic probe sent to Europa, drilling through the thick ice covering the surface of the moon and releasing a submersible into the ocean below. As the submersible explores the dark, icy waters, it discovers strange organic molecules and eventually encounters living organisms, perhaps microbial life forms, or even more complex creatures similar to Earth's deep-sea inhabitants. This discovery would confirm that life can exist in environments drastically different from those on Earth and expand our understanding of where and how life can thrive. This thought experiment highlights the potential for life within our own solar system and the exciting possibilities that lie beneath the icy moons of the outer planets. There are good arguments that life is probably widespread in the universe. The immense number of stars, planets, and potentially habitable worlds suggests that the conditions for life could exist in many places. The discovery of extremophiles, organisms that can survive in extreme environments on Earth, has shown that life is surprisingly resilient and adaptable, thriving in conditions previously considered inhospitable. As we continue to explore exoplanets and moons within our solar system, we may find that life has emerged in many different forms throughout the cosmos. The sheer scale of the universe, with its billions of galaxies and trillions of planets, makes it statistically likely that life exists somewhere out there, even if we haven't discovered it yet. On the other hand, there is the possibility that life is extremely rare, or that the Earth is a unique case. Despite the discovery of many potentially habitable planets, we have not yet found any clear signs of life beyond Earth. The complexity of biological systems and the specific conditions required for life to emerge and develop could mean that life is a rare phenomenon in the universe. Moreover, the lack of evidence for intelligent extraterrestrial civilizations, as highlighted by the Fermi paradox, suggests that even if life exists elsewhere, intelligent life capable of communication or interstellar travel may be exceedingly rare. Whether we find life elsewhere in the universe or not, the search for extraterrestrial life has profound implications for humanity. If we discover that life is widespread, this would suggest that the universe is full of diverse life forms, and that we are just one of many species. This would challenge our understanding of what it means to be human and our place in the cosmic order. Conversely, if we realize that life is rare or unique on Earth, this would highlight the extraordinary nature of life on our planet and remind us of the responsibility to preserve and protect it. The absence of life elsewhere could further highlight the importance of the Earth's biosphere and emphasize the importance of sustainability and environmental protection, the challenges of interstellar space travel, and the limits of human exploration. As humanity gazes at the stars, the question of how we can travel to distant planets and star systems is becoming ever more pressing. The vast distances between the stars, the limits of our current propulsion technologies, and the harsh conditions of space pose enormous challenges for interstellar space travel. In this chapter, we will explore the scientific and technical obstacles to reaching the stars, examine the solutions proposed to overcome these obstacles, and examine the ethical and philosophical implications of interstellar exploration. One of the biggest challenges of interstellar space travel is the sheer size of the universe. While our solar system seems huge, it is tiny compared to the distances between the stars. The nearest star to Earth, Proxima Centauri, is over 4 light-years away. A light-year is the distance that light travels in 1 year, around 9 trillion kilometers. To put this into perspective, even if we could travel at the speed of light, it would take us over 4 years to reach Proxima Centauri. However, no spaceship is currently even close to being able to reach such speeds. The fastest spacecraft ever launched by mankind, NASA's Parker Solar Probe, travels at a speed of around 700,000 kilometers per hour. Even at this speed, it would take over 6,000 years to reach Proxima Centauri. It is therefore obvious that the technology required to make interstellar space travel feasible must go far beyond what we currently possess. To overcome the vast distances between the stars, scientists and engineers are researching a variety of advanced propulsion technologies. Each of these concepts offers potential solutions to the challenges of interstellar spaceflight, although many are still speculative or in the early stages of development. The rockets that took us to the Moon and Mars are powered by chemical reactions, such as the combustion of liquid hydrogen and oxygen. Although chemical rockets are effective for launching spacecraft into orbit and traveling within the solar system, they are not efficient enough for interstellar travel. The amount of fuel required to reach even the nearest star with chemical propulsion would be prohibitively large. An alternative to chemical rockets is ion propulsion, in which electric fields are used to accelerate charged particles, known as ions, to high speeds. Ion propulsion is far more fuel efficient than chemical rockets, and spacecraft such as NASA's Dawn mission have successfully used this technology to travel between asteroids in the solar system. However, the ion drive only generates a small amount of thrust, which means that it takes a long time to reach significant speeds. While ion propulsion could be useful for long-term missions within the solar system, it is probably not sufficient on its own for interstellar space travel. Another potential solution is nuclear propulsion, which could offer a much higher energy density than chemical or ionic propulsion. Two main types of nuclear propulsion have been proposed: nuclear thermal propulsion and nuclear electric propulsion. In nuclear thermal propulsion, a nuclear reactor is used to heat a propellant, such as hydrogen, and push it through a nozzle to generate thrust. This method could generate much higher speeds than chemical rockets. In nuclear electric propulsion, a nuclear reactor generates electricity that is used to power an ion drive or other form of electric propulsion. Although nuclear propulsion is promising, it poses significant technical and political challenges, including the risks associated with launching nuclear materials into space and potential radiation exposure to both astronauts and the environment. One of the most innovative proposals for interstellar space travel is the use of solar sails, thin, reflective surfaces that use the pressure of sunlight to propel a spacecraft. Solar sails do not require fuel, which makes them an attractive option for long-term missions. However, the acceleration caused by sunlight is extremely gentle, so that solar sails would have to be operated for long periods of time to achieve significant speeds. A more advanced version of this concept, known as laser-assisted sails, involves directing powerful lasers at the solar sails to accelerate the spacecraft. This method could theoretically accelerate a spacecraft to a significant fraction of the speed of light. In the year 2016, physicist Stephen Hawking and entrepreneur Yuri Milner announced the Breakthrough Starshot initiative, which aims to develop tiny spacecraft powered by laser-assisted sails that could reach Proxima Centauri within a few decades. Imagine that scientists have successfully developed laser-based solar sails, and a fleet of tiny spacecraft, each no bigger than a smartphone, is launched towards Proxima Centauri. These spacecraft, powered by laser beams from Earth, accelerate to 20% of the speed of light. After a little more than 20 years, the first probes reach the Proxima Centauri system and send back data about the star and its planets. They experience the moment when mankind reaches another star for the first time, not by sending astronauts, but by launching light robotic explorers. This thought experiment illustrates the potential of solar sails and laser-based propulsion systems to reach nearby stars. Although this technology is still in its infancy, it offers one of the most feasible routes to interstellar exploration. Nuclear fusion, the process that powers the sun, has long been considered the holy grail of energy production. If scientists could succeed in harnessing fusion energy for space travel, it could provide an incredibly efficient energy source that would enable spacecraft to reach far higher speeds than chemical or nuclear propulsion. The fusion drive would consist of generating a fusion reaction, similar to that in the Sun, in the engine of a spacecraft. The energy released during fusion could be used to heat a propellant and generate thrust. Despite decades of research, however, controlled fusion has not yet been achieved on Earth, let alone in space. Although fusion propulsion holds great potential, it is still a distant goal that requires considerable progress in both fusion research and space technology. Imagine boarding a fusion spaceship capable of accelerating to a significant fraction of the speed of light. The journey to Proxima Centauri, which would take tens of thousands of years with today's technology, will be completed in just a few decades. As the spaceship travels at relativistic speeds, time dilation effects come into play so that the crew experience the journey in a much shorter time than would be the case on Earth. You belong to a new generation of explorers who are experiencing the journey to another star at first hand. This thought experiment demonstrates the transformative potential of the fusion drive. If humans succeed in harnessing fusion energy, interstellar space travel could become a reality within a few centuries. While the technical challenges of interstellar space travel are enormous, ethical and philosophical questions also arise when we think about sending people and machines to other star systems. One of the most significant ethical concerns is the potential impact on any extraterrestrial life we may encounter. If life exists anywhere else in the universe, be it microbial or intelligent, our arrival could have unintended consequences. Some scientists and ethicists argue that we should proceed with caution to avoid contaminating extraterrestrial ecosystems and respect the autonomy of intelligent civilizations we may discover. The long-term sustainability of interstellar travel also raises questions. Even with advanced propulsion technologies, journeys to other stars would take decades or even centuries. This raises the question of whether it is ethical to send human explorers on such missions in the knowledge that they may never return to Earth or may not complete their journey within their lifetime. The immense costs of interstellar missions must also be taken into account. While the pursuit of knowledge and discovery is a noble goal, some argue that resources could be better used to solve pressing problems on Earth, such as poverty, climate change, and biodiversity conservation. For many, the exploration of other star systems represents the next great frontier for mankind. The urge to explore is deeply rooted in our species, and interstellar space travel represents the ultimate expression of this drive. By pushing the boundaries of our technological capabilities and venturing beyond the solar system, we can expand our understanding of the universe and potentially discover new life forms. Interstellar exploration could also serve as a safeguard for humanity. In the distant future, should Earth become uninhabitable due to natural disasters, climate change, or other factors, the establishment of colonies on other planets or in other star systems could ensure the survival of the human species. On the other hand, critics argue that the dream of interstellar space travel is impractical or even dangerous. The enormous distances and the limits of our current technology make it unlikely that humans will reach other stars in the near future. Some critics argue that the resources and attention devoted to interstellar exploration could be better used to tackle more pressing challenges, such as protecting our planet and ensuring the sustainability of human civilization on Earth. Furthermore, the ethical challenges of interstellar space travel, such as the potential disruption of extraterrestrial ecosystems, cannot be ignored. As we venture into space, we must grapple with the question of whether we have the right to colonize other worlds and what responsibility we have to any life we might encounter. Despite the daunting challenges of interstellar space travel, the potential rewards are enormous. With the advancement of technology and our growing understanding of the universe, humanity may one day develop the means to travel to other star systems. Whether through fusion propulsion, solar sails, or other as yet unimagined technologies, the dream of exploring distant stars remains a powerful driver for scientists, engineers, and explorers. For now, the search for life on exoplanets and the development of robotic probes offer the most promising ways to extend our reach beyond the solar system. But as we continue to push the boundaries of exploration, the possibility of humanity one day undertaking interstellar travel will remain an exciting and tantalizing vision. The future of human evolution, adapting to life beyond Earth. As humanity looks towards the stars and contemplates the challenges of space travel, one question is becoming increasingly relevant. How will humans evolve as we go deeper into space? The space environment is radically different from Earth's, and long-term exposure to microgravity, radiation, and isolation could have profound effects on the body and mind. In this chapter, we will explore the potential of human evolution in space, the biological and technological adaptations that may be required for life on other planets, and the possibility that the next chapter of humanity will be written not on Earth, but among the stars. Space is an inherently hostile environment for human life. The Earth's atmosphere provides protection from harmful cosmic radiation, while gravity ensures that our muscles, bones, and organs function normally. In space, however, the lack of gravity and the lack of protection from radiation led to considerable health challenges for astronauts. One of the most immediate challenges of space travel is the effect of microgravity on the human body. In the weightless environment of space, astronauts experience a number of physiological changes, many of which are harmful to their long-term health. Without the constant pull of gravity, muscles and bones begin to atrophy. Astronauts who spend long periods in space often suffer from muscle atrophy and loss of bone density, as their bodies no longer have to support their own weight. In addition to the loss of muscles and bones, microgravity also affects the cardiovascular system. The heart, which normally works against gravity to pump blood around the body, does not have to work as hard in space. Over time, this can lead to a weakening of the heart muscle. Fluid distribution in the body is also affected, with more fluid accumulating in the upper body and head, resulting in a space face, a puffy appearance, and increased pressure on the eyes, which can cause vision problems. To counteract these effects, astronauts on the International Space Station, ISS, have to train for several hours a day to maintain their muscle mass and bone density. Despite these measures, long-term space travel poses significant health risks that need to be addressed if people are to live and work in space for long periods of time. Another major problem in space travel is exposure to cosmic radiation. On Earth, we are protected from most harmful radiation from the sun and the cosmos by our planet's magnetic field and atmosphere. In space, however, astronauts are exposed to much higher levels of radiation, which can damage cells, increase the risk of cancer, and cause other health problems. The risk of radiation is particularly acute for missions beyond low Earth orbit. Astronauts traveling to the Moon, Mars, or other destinations in the solar system would be exposed to much higher levels of cosmic rays and solar radiation than those working on the ISS. Prolonged exposure to this radiation could have serious consequences, especially for missions lasting several years. Scientists are exploring a number of solutions to this problem, including improved shielding for spacecraft, the development of protective materials, and even the possibility of using water or other substances to block radiation. But finding a way to protect astronauts from radiation remains one of the greatest challenges of interplanetary space travel. Imagine you have been living on board a space station for several years. You have become accustomed to life in microgravity, where everything floats and you have to use handrails to get around. Although the absence of gravity initially felt liberating, you noticed that your muscles became weaker and your bones lost density. Despite daily training, you feel the effects of long-term weightlessness. Wondering what long-duration space travel will mean for future generations of space travelers. Will they adapt to microgravity over time? Or will human biology need to be fundamentally altered to survive in space? This thought experiment illustrates the challenges of long-term life in space. While we can adapt to microgravity in the short term, the long-term effects on human health are not yet fully understood, and future space explorers may need new solutions to thrive in these conditions. The more time humans spend in space, the more likely we are to undergo evolutionary changes to adapt to the new environment. Evolution is driven by environmental influences, and the unique conditions of space, such as microgravity and increased radiation, could lead to changes in the human body over the course of many generations. Although natural evolution requires long periods of time, the accelerated pace of space exploration raises the possibility that humans could adapt to space more quickly, through artificial means. This could involve genetic engineering, where specific genes are modified to help future generations of humans better cope with the challenges of space, for example, through radiation resistance or the ability to maintain muscle and bone mass in microgravity. The field of genetic engineering has already made significant progress, and techniques such as CRISPR are enabling scientists to edit DNA with increasing precision. In the future, these technologies could be used to improve human biology for space travel and enable astronauts to better endure the rigors of space and even colonize other planets. Imagine a future in which humans have been genetically modified so that they can thrive in space. These space-adapted people have increased bone density, radiation-resistant skin, and the ability to live in microgravity without suffering muscle atrophy. As these individuals travel to distant planets and moons, they represent a new branch of human evolution, specially adapted to life beyond Earth. What ethical questions would arise from this form of genetic modification? Would these space-adapted humans still consider themselves fully human, or would they represent a new species? This thought experiment raises important questions about the future of human evolution and the role of genetic engineering in space travel. While such technologies could improve our ability to explore the universe, they also bring with them ethical and philosophical considerations. While genetic engineering offers a potential pathway for human adaptation to space, technological advances could also play a crucial role. As we explore the possibility of colonizing other planets, we may need to develop technologies that allow us to create artificial environments that mimic Earth's gravity, atmosphere, and other conditions necessary for human survival. One potential solution is the use of rotating space habitats that generate artificial gravity through centrifugal force. These habitats, often referred to as O'Neill cylinders or Stanford Torrey, could provide a stable environment in which humans could live and work for extended periods of time without experiencing the harmful effects of microgravity. In addition to artificial gravity, other technologies are also needed to sustain human life on other planets. For example, terraforming, altering a planet's environment to make it more Earth-like, has been proposed as a long-term solution for colonizing planets like Mars. While the concept of terraforming is still speculative, advances in climate science, biotechnology, and robotics could one day make it possible to transform barren worlds into habitable environments. The idea of colonizing other planets raises important ethical questions. When we think about sending people to Mars or beyond, we have to ask ourselves, do we have the right to change the environments of other worlds? If we find microbial life on Mars or other planets, should we prioritize the preservation of these ecosystems over human colonization? Another question is whether humanity should focus on protecting the Earth before turning to the stars. Some critics argue that humanity should solve its environmental and social challenges on Earth before attempting to colonize other planets. Others, however, believe that space exploration and the establishment of colonies beyond Earth could yield valuable knowledge and technologies that improve life on our home planet. Imagine you belong to the first generation of people to live on Mars. You live in a large, pressurized habitat station designed to mimic Earth's environment, with artificial gravity, a controlled atmosphere, and advanced technology to produce food and water. Over time, the colony grows, and you begin to terraform the planet by gradually changing its atmosphere and temperature to make it more habitable. When you look at the red Martian landscape, you wonder whether humanity has the right to change another world. Will future generations call Mars home, or will they always long for Earth? This thought experiment illustrates the challenges and ethical considerations associated with colonizing other planets. While Mars offers a potential home for future generations, the question of how we interact with other worlds remains unanswered. Proponents of space travel and human evolution in space argue that humanity must evolve, whether through natural selection, genetic engineering, or technological improvements, in order to survive and thrive beyond Earth. The further we push the boundaries of space travel, the more urgent the need for new adaptations becomes. Evolving to live in space could be the key to ensuring humanity's long-term survival. On the other hand, some critics warn against the use of genetic engineering and other technologies to modify human biology for space travel. They argue that the risks of unintended consequences, both biological and social, are too great. Altering human DNA could have unforeseen effects on future generations, and the ethical implications of creating enhanced humans must be carefully considered. There is also concern that the focus on human adaptation to space could divert attention and resources away from solving challenges on Earth. As humanity continues to explore space, the question of how we will adapt to life beyond Earth is becoming increasingly important. Whether through natural evolution, genetic engineering, or technological innovation, humans will have to find ways to overcome the challenges of space travel and colonization. The future of human evolution in space offers exciting possibilities, but also raises profound ethical and philosophical questions. As we move forward, we must carefully consider the implications of changing human biology and the responsibility we have both to our own species and to any life we might find beyond Earth.